Alright, what else? And. Let's see if I've got enough room to put that. No, I don't. So we want probability of A and B now. How do we figure that out? So we want the event A and B. What does that mean? So we want those faces of the die that satisfy both events. Alright? So both we have, remember, A is 2, 4, 6 and B is 3, 4, 5, 6. So those that satisfy both, we have 4 in both and 6 in both. Alright, so if we get either a 4 or a 6, we satisfied both events. So the probability of the event A and B is 2/6, 1/3. Okay, so now we can go back and sort of running out of room for the whole screen here and talk about the addition rule. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. As we'll see in a little bit, that's the overlap. So the probability of A is, well, let's keep it in sixths, 3/6 plus the probability of B, 4/6 minus probability of A and B, 2/6. Alright, so 3 and 4 is 7 minus 2 is 5. So the probability of A or B is 5/6, and that's the number we found before. Alright, so that's the addition rule. It works for simple events like this or more complicated, any events that we might have. Another way to think of this is with something called a Venn diagram. Venn is a guy's name. Okay, and in this box are all the events that can occur when we roll the die once. So we have, say, event A and B. Let's make sure I get this right. So A is 2, 4, and 6, and B is 3, 4, 5, and 6. Okay, and there's one face of the die that doesn't show up in either A or B, and that's a 1. Alright, that's a Venn diagram. So, over here, A and B, if we're looking for A or B, we're talking about the whole thing. Okay, if we're talking about A and B, we're talking about the overlap. Okay. Alright, so that's the addition rule. So the basic concept behind the addition rule is that we could add the two probabilities together, A and B, but when we do that, alright, if we just focus on that first part, we forget about the overlap. Alright, so if we add the probability of A together, alright, this part, probability of B together, what we get as an answer in this, for this example, is 7/6. Well, that's greater than 1, and we know that's not right. And our error is that we've added the overlap, so we take the overlap off. Alright, so this part we take off and we get our answer 5/6. The next important concept or idea is selection. Or you can think of the word down the road, sampling, with or without replacement. Now realistically, down the road, when we're talking about sampling theory, we're always sampling with replacement, but there are sometimes in the world where we sample without replacement. Okay, so we need to look at both of those. Sometimes in the real world, though, we have to sample without replacement. If we're testing certain products, for instance a light bulb, and testing it till it fails, we're sampling without replacement, all right? Because once the light bulb has failed, we can't put it back in the population for the possible reselection. Okay. Anyway, so most common situation with replacement. It's always good with anything that you learn is to understand a very simple case, and from the simple case work to the larger, more difficult case, and it's that way better for your memory too. So a simple case with replacement is a coin toss, and you're thinking to yourself, what am I replacing here? Well, you're not really replacing anything, but when you sample a coin, you're not taking anything away either, so it can be a head or a tail, and if you get a head on the first toss, the head doesn't disappear, and so that you're left with just a tail in the next toss. All right, so that's with replacement. Without replacement, simple example for you to latch on to is candy in a jar. And when you pick, select, sample a piece of candy, it stays out, never to be returned. So you can imagine that you eat that piece of candy. Okay. Alright, so let's look at with replacement first, and again the very simplest example. And talk about probabilities for such events. Alright, so we're going to toss a coin 2 times. Or another way of getting the same outcome is to have two coins and toss them at the same time. But tossing a coin 2 times gives you the idea of sequential events. Alright, so sequential events are important. Alright, so remember that the probability of a head on any one toss is a half, and the probability of a tail on any one toss is a half. And since we're selecting with replacement, the probabilities don't change. Doesn't matter if it's the first toss or the 100th toss, the probability of a head is a half, probability of a tail is a half. Alright, so let's look at the following probabilities. Let's say if I wanted a probability of a head on the first toss and tail on the second toss. Alright, so just for notation, I would write that probability H1 T2, right? Head on the first, tail on the second, these sequential events. So down the road I might write actually HT, right? And they written down in the order that they appear. The way we do this is with the following: the probability of a head on the first times the probability tail on the second. Alright, so the probability of head on the first is a half times probability of tail on the second is a half, and the answer for that is a quarter. Again, the answer is not, the final number is not crucial here, it's the concepts, right? It's a half on the first, half on the second. So what if I get, what's the probability of, say, head on the first and a head on the second? Right? Probability head on the first times the probability head on the second. Again, a half times a half is a quarter. It's the probability of no heads in 2 tosses. Well, it's actually probability of tail on the first, tail on the second, right? Probability tail on the first times tail on the second. It's a half times a half. Quarter again.